This talk, I'll talk about the Lens project on verifying evolving software. So let me first acknowledge a large number of external collaborators that we were happy to work with, both in industry and academia. So the overview of the problem, what we're interested in, our sort of long-term goal, is to verify evolving software, where we want to understand evolving in a most general sense. So software that's evolving because somebody is changing it and updating it and fixing it, or evolving because it's reacting and it's adaptive and it's reacting to its environment, or software that's evolving through, say, compilation chains, so sort of similar to what Sagar was showing. And that's actually the target that we had in this particular lens. What our ultimate goal is to make verification, re-verification effort small comparable to the amount of change that has happened. Now, of course, this is sort of a well-known problem in verification. Everybody wants verification that's very efficient and very incremental. And there are many current solutions, but they're all very limited. Either they have unrealistic assumptions. For example, some require programs not to have any loops. Or they're just based on very strict syntactic restrictions. So let me first start with our case study. So in order to drive this research, we picked a model problem, which is a certifying compiler for the C programming language. And the difference between a normal compiler and a certifying compiler is that a certifying compiler has a verifier inside of it. It takes a program and a property, typically expressed as different assertions. And then at the end of the day, when it constructs a binary, it also outputs a certificate, why you should trust this binary. And the benefit of a certifying compiler is that you don't have to trust the compilation chain. It can be very complicated, but as long as the last check passed and a certificate is generated, we know that the result is correct. Now, when we look at this architecture, so this is fairly complicated, but there are important things to know. There's a front end, and that's something that's fixed and exists in many compilers. There's a verifier and a compiler, and both of these components we have. So we've been working on a verifier for quite a number of years, and a compiler, we use a standard off-the-shelf compiler, in our case, LLVM. But in order to make this whole thing work together, we need to have these two chains. We need to move from the front end into the verifier. This is the simplify box in the picture. And then once the verifier gives us a certificate, we need to bring the certificate back. We need to adapt it back towards what a compiler can understand. So this adapt box is sort of the focus it's a model problem for our lens. We've divided our work into 5 research tasks. The first 2 are the main tasks that we've done, and the other 3 were smaller projects that we did as well. So the first one is we looked at verifying 2 particular optimizations in LLVM. One called ins combine, and another called simplify CFG. So this is 2 main optimizations. The ins combine one modifies things inside the basic block, and simplify CFG modifies the control flow graph. Typically, they run in pairs. So you run one, then another, then one, then another. And that's responsible for majority of optimizations. And so we looked at how can we move verification certificates across these optimizations. Now, the second project is we looked at closing the semantic gap between a compiler and verifier. And I've picked just this project to give you more details about. So I won't talk about it just now, but I'll give you a few details in a few slides. And then we looked at sort of tools that are needed for this. One was minimizing certificates, because the smaller the certificate, the easier it is to transfer. We also looked at extending the certifying compiler, not to start from C, but from Illuster, which is a higher level programming language used by NASA in their flow when they start from Simulink models and then go down to executable code. And then we looked at improving how we generate certificates, which was the last project. Okay. So here's sort of, every time we approach this problem, we follow these 4 steps. This is our main adaptation approach. So we start with assuming that we can compute the certificate for the original program P1. We then evolve the program from P1 to P2 by some change. Then we adapt the certificates from the old program into a new program. And then we strengthen that certificate if necessary, if it's not really a complete certificate. Now, the steps may look very simple, but the important thing to know is sort of the step 1 and 4 are enabled by our ongoing work on verification. And namely, they're enabled by our recent breakthroughs in building verifiers that can produce certificates and can take certificates and start from them and only do the extra verification necessary. So the focus here was, given those technologies that we already have, how can we develop an adaptation that would work with them? Okay. And so as I said, I'm just trying to illustrate this on this particular project of closing the semantic gap. Okay, so what's a semantic gap? Whenever we think of a program, we think a program is written in C. We understand what it's doing. But that's not how the compiler and verifier sees it. A compiler typically looks at the program in some intermediate code that represents some form of machine instructions. In particular, a compiler knows that every number is represented by number of bits. Not every number is representable. There's an overflow, underflow, and lots of other things that can happen. And it uses all of this to make the program go faster. On the other hand, when we go to a verifier, we make a sort of unrealistic assumption that we can represent what the program is doing using arithmetic constraints. And we can represent every number exactly as it is in arithmetic. And that's what our verifier is doing. And the difference between the two, that's the semantic gap. The compiler and the verifier don't talk about the same things. Now you may say, you may think that, well, maybe the verifier can be improved and can work over machine code directly, that maybe just the verification people are lazy. But there's a fundamental difference here, that there are verifiers that work on machine code. We actually have one. I'll show how we're using it. But going to machine code make verifier really, really slow. So all of the scalability is achieved by representing the program in arithmetic and then using complicated mathematics in order to show how you can reason about it very, very quickly. If we go to machine code, we don't have the theories that we need in order to do that. So we start with this. And this is a solution that we've developed. And the idea is to adapt the result of a scalable but imprecise verifier to a precise certificate over a program. So we start on the left with the source code, represented by constraints, give it to our scalable verifier that talks about arithmetic. It gives us an arithmetic certificate. And then we go into our adapt box. In our adapt box, what we do is we reinterpret certificate relative to machine integers. And then we do extra check to see which part of it are now violated and which part still works. And what comes out is a precise invariant. And that goes into our precise verifier that has precise semantics but is very slow. But now it doesn't have to reason about the whole program, but only about the part of it not covered by the invariant we already have. And then it outputs a precise certificate. And so when we finish this, we get so excited about it because it seemed to work so well that we decided to turn it itself into its own tool. So we built a tool called Frankenbit, which is a bit-precise verifier. And what it's doing, it's combining two tools. So we have an approach of how to prove a program correct. Of course, not every program is correct. So we've taken off-the-shelf tool that looks for bugs in the program. And what our tool does runs these two things in parallel. Either we find a bug, and then we stop, or we manage to generate a certificate, and then we stop. And we've submitted this to the software verification competition, which is becoming sort of one of the standard venues where we can evaluate this kind of tools in a rigorous way. And what we found out is that the results were just really amazing for us. So we got a silver medal and a bronze medal. But what's more interesting, when we look, I mean, you can't see these graphs, but when you look at them carefully, you see that for this particular examples, our adaptations are going from unsound to a completely sound and precise result has very little cost. So the difference, say, between the third place Frankenbit and the second place UE4, which are both of our tools, is very, very small in terms of time it takes to solve each benchmark. Okay. So let me just conclude with summarizing the outcomes that we have. So we've developed 3 tools. One is Frankenbit, which I just showed. I also developed a tool called Niagara that uses similar ideas, but in order to move verification across optimizations done by LLVM. Again, it's the same 4 steps, but then the way you adapt things are quite different because the challenge with an optimizer is figuring out how new names created by a compiler are changed, are mapped to the old names that were there before. And then we also collaborated with researchers at NASA Ames to develop a tool called Zuster, which is a verifier for the Lustre programming language. So this is sort of a higher level programming language for which we also want to have a certifying compiler. If you're interested in any of the things that I haven't talked and just mentioned here, I'll be here after the talk, so please find me and I can tell you. And if you're interested in reading more about it, there's a number of publications that describe the details of the tools. Thank you.